There are 4 changes for pressure volume work. There are 2 listed here, isobaric change and isovolumetric change. Isobaric means the pressure will not change, and isovolumetric means there's no volume change. Now, before we get started with any pressure volume graph, we always have to do pressure volume is equal to nRT, which of course is our Pivnert equation as it's called. This we use to find the temperature. So if we have an isobaric change, let's say we start at this position here and end over here, we'll use a dotted line to represent that change. So what we notice is that the pressure stays the same while the volume does change. Now, of course, we will have pressure volume work, and work is just going to equal pressure times the change in volume. Okay, the change in internal energy, of course, is a sum of heat flow. Now, that'll be a heat flow at constant pressure, okay, and work done. So how do we calculate heat flow? Well, we need a molar heat capacity. So we have heat is equal to N, which is your number of moles, times the molar heat capacity at constant pressure, times the change in temperature. Okay, now how do we get the molar heat capacity? Well, that would be Cp is equal to, let's assume we have a monatomic gas, so that would be 3/2 R plus R. R, of course, being the gas constant, 8.31. So the change of internal energy in this case would then be pressure volume work, which is W, okay, plus the heat flow at constant pressure. Okay, now what happens in this case? If we expand the gas, that means the temperature has to increase. Therefore, heat flow is positive and pressure volume work is negative. Now, what if we contract the gas? Okay, well, that means the temperature will go down. So temperature decreases. So the work would then be positive because work is being done to the gas, and then the heat flow is negative as heat escapes. And again, delta U is a sum of both of those processes. Okay, now what about isovolumetric? That means the volume does not change. So let's say I start at this position here. I would then end in the position here. And we'll use the dotted line to represent the change that's existing there. Now here, work is going to equal 0. Okay, since there is no pressure volume work done, there's no volume change. Okay, therefore Q is going to be a Q sub V, which means heat flow at constant volume. So therefore, the change in internal energy is going to equal heat flow at constant volume. So how do we calculate that? Well, that would be Q equals NCV delta T. So we use the molar heat capacity for constant volume. Now what does that equal? Well, again, we'll assume a monatomic gas. So CV is just going to equal 3/2 R. So again, by definition then, change in internal energy is equal to heat flow at constant volume, which indicates that the change in internal energy is temperature dependent. So that always depends on temperature. Now let's relate this to something else. An isobaric change is really Charles' law. Volume 1 times temperature 2 equals volume 2 times temperature 1. So that might be more familiar to you. Now what about isovolumetric? That's Guy-Lussac's law. So pressure 1 times temperature 2 equals pressure 2 times temperature 1. So that might help you understand this in a little bit better fashion.